In this video I'm going to show you how we use QR decomposition to solve a linear system. So solving linear system with QR. QR decomposition. Okay. Right, so if you've seen the previous video, which I suggest you look at if you haven't yet seen it, so I'm just picking a colour. Okay, so we looked at a previous video. We looked at using QR decomposition to rewrite A as the product of Q and R. Now Q is an orthogonal vector, which has some nice properties. Vector is orthogonal matrix. Now R is just an upper triangular matrix. Okay, so if we wanted to solve a system of the form AX equals B, that's our standard linear system. So if we rewrite A as QR, and we got QRX equals B, what we can do is we can, if we inverse both sides, we can write RX equals QB. Now a very nice nice property of orthogonal matrix is the inverse of Q is equal to the transpose of Q for orthogonal matrices. Okay, so that means, oh, that's meant to be inverse, so that means we can rewrite that as QTB. So the solution for our linear system of equations is just a simple matter of solving Rx equals QTB, or Q transpose times B. Now this, if we were to write this down, let's say I've got R1100, let's say we write that down for a 3x3 system, so R12, R220, R13, R23, R33. Okay, and that's multiplied by, let's say, yeah, if we got a 3 by 3 system. Now Q, so Q will have 3 columns. Let's say there's 3 columns there, so Q1, Q2, Q3, and that's multiplied by B. So that's going to be multiplied by all the B's, so B1 all the way down to however many B's we have. Okay, so this is a upper triangular matrix, so we can solve this using back substitution. Okay, so it's just a single Kraut's method for use with LU decomposition or Cholesky decomposition required a forward to solve for your vector y and then a back substitution to solve for vector x. With QR decomposition we only needed a backwards substitution to solve. Okay, so let's have a look at an example. So I'm going to have a look at example from the notes, which is 6.16, and the system we're going to solve is, well, the coefficient matrix will look fairly familiar to you if you looked at the video on calculating QR via Gram-Schmidt. So we have this 4x3 coefficient matrix. We're going to have 3 unknown values for x, and we're going to have 4 constant values in our vector. Okay, so this is an example of an over-determined system. We've got more equations than unknowns, but we can solve this using QR decomposition, and in a previous video we determined what Q and R were, so I'm just going to rewrite them here just to remind us. That's meant to be a half. Oh, don't know where that third came in. Why did I write a third? There we go, a half. And R was 242.028.004. Okay, so remember we solve Rx equals QTB. Okay, so we got, on the left we've got 242.028, so that's our R matrix. and that's multiplied by our unknown values x1, x2, x3. Now on the right, so the transpose of q is going to be a 3 by 4. It's going to be minus a half, minus a half, a half. And the second row is just going to be all halves. And the third row is going to be minus a half, 1 half, 1 half. And that's going to be multiplied by our 4 by 1 constant. Okay, so if we calculate that, okay, so this is a 3 by 4, this is a 4 by 1, so we're going to end up with a 3 by 1 vector, which is 18, 32 and 12. Okay, so we're going to use back substitution to solve for x1, x2, x3. Okay, so starting off with x3, the coefficient of x3 is 4, so we're going to have 1/4, and the right hand side value b3 is 12, so that's going to give us 3. Solve for x2, coefficient of x2 is 2, so that's going to be 1/2, and we have 32, so that's the second value of b, minus 8 times whatever x3 was. Minus 8 times 3, that's going to be 24, so that's going to be 8 divided by 2 is 4, and x3, coefficient of x3 is going to be 2, sorry, x3, I mean x1, coefficient of x1 is 2, so that's 1/2, so that's going to be 18 minus 4 times x2, so that's 18 minus 16, that's going to be 2, minus 2 times x3, so minus 6, so that's going to be minus 4 divided by 2, that will give me minus 2, and that's your solution using QR decomposition.